Okay, so welcome back to Particle Physics and the Standard Model. This is lecture 32, and in the previous lecture we started putting together the Standard Model in a very real way, right. We made use of all the ingredients that we learnt about gauge invariance and of course Lorentz invariance, wrote down a generic Lagrangian transforming under an SUN gauge group, and we saw how to implement this in the real world by first defining the fermion content and seeing how each of these spinors transforms internally under each of the these gauge groups, right. So, we saw there was QUD which were charged under color, the Q is left handed and so it is charged under SU2. And we also had the lepton fields L and E, the L is a doublet under SU2, the E is not, right. And so we represented that with vertices, interaction vertices as well, just to be clear, and we wanted to understand what interactions actually these fermions took part in. The obvious interaction to write down was using the covariant derivative, we wrote down all the gauge interactions, correct, which is a Lagrangian representation of the vertices that we just drew here, correct. But that is what made us wonder what happened to the fermion masses, and we concluded by saying that you do not even have a mass at this point, because that would mean to have a Lorentz invariant structure you have to necessarily marry left handed fermions with right handed fermions, right. This we had seen when we constructed the spinor Lagrangian, right, after solving the Dirac equation, right. If you do not remember, please go back and look at those lectures again. This term, the mass term, could only be written down if a left and right handed fermion were married with each other, but that is explicitly forbidden now by the fact that the SU2 gauge only acts on the left handed terms, on the left handed spinors, right. That would mean if I write a mass term, then this does not satisfy gauge invariance, the SU2 gauge invariance, right. That is the reason why we say that the SU2 gauge actually forbids fermion mass terms, you are forced to be in a massless fermion theory, okay. Now let us take this further, okay. What about gauge boson masses? Remember when we wrote the Proca-Lagrangian, right, remember we had this, right, and I had a mass term, that is necessarily what made it a Proca-Lagrangian, correct, and we saw that this was gauge invariant and this was gauge invariant, and so the entire term is doubly gauge invariant, whereas this is not gauge invariant, right. Remember this. So, in other words, that implies that if I want gauge invariance as part of my theory, okay, that necessarily means the gauge bosons are also massless. Isn't this funny? We have just constructed a completely massless theory, okay. All the ingredients that we put in, all the force carriers and the force feelers, they are all massless actually, but obviously we are not living in a massless world, right. Everything has a mass. So, how do we do this? How do we construct a consistent theory, a theory where particles have a mass at the fundamental level, okay. That is really the very central point of the Standard Model and Delta-Weak symmetry breaking, okay. So, this is where we have to introduce yet another field. What is this field? The very famous Higgs field, okay. Now, how do I define the Higgs field? I am going to use the same notation as here under SU3 and SU2 and the hypercharge. Let me right away write this in red. The Higgs field transforms as a 1, okay. Most importantly a 2, it is a doublet under SU2, it feels the weak force, okay. And finally the hypercharge turns out to be 1, okay. That is the field, okay. Now if those are the quantum numbers of the field, so that terminology is clear, right? Quantum numbers, I just mean what is the, how does the field transform under each of the groups. If those are the quantum numbers, then you will see that I can write one more piece of the Lagrangian, okay. I am going to call it a Yukawa Lagrangian, that is why I am writing Yuk, okay. And I can now absolutely make use of this vertex, okay. Of course, I have to be a bit more careful. I am going to put a dagger here. This is all again, this is all in 2 fermion notation, 2 spinor notation, okay. So this is left handed field, right handed field. You see what I have done here, this is just like, you know, playing Tetris or, you know, fitting Lego blocks. So what have I done here? I need to make sure that the you know, the 2, right, first of all I need to make sure that the color is satisfied, that this whole term is invariant under color. Is that true? It is manifestly true because there is no colored fields that we started with anyway, okay. So that is satisfied. What about the SU2? So this, the L field transforms as a doublet under SU2, the H field also transforms as a doublet under SU2. So I have just you know, married a doublet under doublet and I am going to get a singlet, correct. This is going to be a row matrix, this is going to be a column matrix, row matrix, column matrix, right. Or in other words, this is in the anti-fundamental representation. So LL dagger will be a 2 bar under SU2, H will be a 2 under SU2 and they cancel each other basically, okay. And finally the hypercharge. What is the LL's hypercharge? It is -1, right. So LL dagger has what hypercharge? LL dagger has +1. The Higgs I just said literally has +1 and ER we gave it -2, right. So -2, okay. So this is what I mean by like playing Tetris or Lego. We just fit all the charges together and form a complete singlet, okay. This is also part of the art of writing a Lagrangian, writing terms that satisfy all the symmetries, okay. But I am not done yet, okay. There are so many things that I have missed in this. What have I missed here? First of all, okay, I should write a coupling, right. I am going to introduce a whole new coupling. A Lagrangian should contain a coupling, right. So to keep the energy is positive definite, I am going to put a minus in front, but also its convention, okay. And I am going to call this coupling Y. In fact, because this coupling is the one that marries the Higgs field to leptons, so it is called YE, okay. This is a completely undetermined coupling, just like the gauge couplings, right. Also, this is not the gauge coupling. Notice that this did not come from any gauge redundancies and there is nothing here in the adjoint representation or anything like that, right. This is all in the fundamental representation. It is just a term that you could not help writing down, okay. That coupling is called the Yukawa coupling. Every time you hear the word Yukawa, think of 2 spinors and a scalar, okay. That's literally how Yukawa predicted the existence of a meson of the pion, right? Because he wanted the pion to be the mediator in the strong force between two nucleons, right? Okay. What else are we missing here? One final thing we are missing here is flavor index. Remember, there are three flavors, not three flavors, three generations, the generation index, right? So, generally, any of the three generations of the L field can hook up with any of the three generations of the E field through the Higgs way. That means what I have here is not one coupling but a matrix of couplings. Okay. In other words, I have how many YIJs? I have 9 YIJs, 9 Yukawa couplings here. Okay. These are not extraneous details. These turn out to be the most important details as we go along in the course. Okay. So, please do pay attention here. This is exactly what would lead to things like oscillations and mixings in the masses, CKM matrix, flavor observables, and so on and so forth. Okay? Good. Now, can't I write a similar term involving the quarks? If I put a QL, what should I put over here? So, first of all, you agree that the SU2 charges are eaten up, the Higgs and the QL fields eat up the Higgs SU2 charges. Now, I still need to write something to eat up the color charge, correct? So, I have two options now, correct? I can either put in a UR or a DR, and you will agree with me that if I want the hypercharge to be correct, to work out correctly, I need to actually put in the DR charge, right? So, let me write that down, the DR field. Okay. So, once again I am going to write down the hypercharge. Of course, this is the QL dagger, most important, right? So, I am going to write down the hypercharge. For QL dagger, it is -1/3. For the Higgs, it is 1. For DR, it is what? It is -2/3, and that is 0. Good. So, that checked out. Okay. And of course, once again I have to write the flavor indices. So, that is what I am doing here, and I have let me write that in blue, Yij. But now, since this is unique to the quarks, I might as well call this Yd, okay, because only the D quark has come along for a ride here, right? Okay, excellent. So, let me just be very clear, the I and J are flavor indices. Very good. Okay, so we have started writing down let me put the name up so it's clear. We are basically exploring the Yukawa sector of the standard model. we already explored the gauge sector. Now we are exploring the Yukawa sector. Okay, these are all terms that are good to have in mind because it helps you organize your thoughts about the standard model. Okay. Now, let me write it over here. What about the coupling of QL dagger UR to the Higgs field? Can you do this? So, we just saw QL dagger dr we did. What about this combination, right? If you have dr, you would think by the same token you also want an interaction with the ur, right? The problem here is, look at the hypercharge, right? So the total hypercharge of this object is what? Over here it is what? So it is for QL, or at least for QL dagger, it was minus 1/3, and for UR it was 4/3, right? So minus 1/3 plus 4/3, what is that? It's 1, correct? Now what is the hypercharge of the Higgs? That is also 1, right? So if I just wrote QL dagger HUR, right? What is the hypercharge of this object, this entire object? That would be 2. But we want the total hypercharge to be 0, right? So what do we do now then? How do we marry the Higgs to this combination in particular? So we are going to make use of a trick. Okay, so bear with me here. These are all important tricks, and this is exactly how we get masses for the quarks. So okay, so it's important to look at what's going on here. Let me define, okay, a field in terms of the Higgs field only, but as a H star. Okay, you can see where I am going with this, right? Because if I have an H star, what is the hypercharge of a H star? That's minus 1, right? So if I somehow have a term that looks like QL dagger H star UR, right? Okay, if I have this, then the total hypercharge is 0, right? Plus 1 plus minus 1 minus 1 basically, right? So my object is to construct a term like this, but it's not really this. Okay, why? Because this term is not yet, okay, SU2 invariant. It's not yet gauge invariant under the SU2. I have to do something slightly different in order to get an SU2 invariant term. And it turns out that that slightly different thing is this, and it will become intuitively clear when I work out what happens under SU2 transformations. Okay? If that is the case, first of all, you will also agree that the hypercharge of the H tilde field is also minus 1, because you know the Pauli matrix obviously doesn't carry any hypercharge. So H star's hypercharge is what it is. Okay, so that is what I define as my new field, if you want to call it that. Okay, then I can now write down one more term here. Okay, this time I am going to just write the flavor indices right away, because you know it's coming. So I have a Q, L of course, a dagger, then I have the H tilde and the right handed field. Okay, and finally, what have I missed here actually? Is the Lagrangian a real entity or a complex entity? It is real, but generically everything we written down here is complex, right? All the fields are complex, even the couplings could be complex, right? So plus the Hermitian conjugate. Okay, never forget this. You should always write the Hermitian conjugate. Always think about complex versus real. Okay, and I claim that this term, right, is SU2 invariant. Okay, and let's verify that claim right now. Okay, how do we do this? There's a simple way to do this. Okay, take infinitesimal transformations of the fields under SU2. Okay, so this you can do in terms of the generators, right? So if I have an infinitesimal change parameterized by this theta, it's like an angle, right? This is an infinitesimal amount by which I transform the field. What should I hit this with? So I'm going to write a j here as an index so that you don't confuse it with the I outside. I should hit this with the generator, no, the polymatrix times 2 divided by 2, right? So that's my infinitesimal transformation. Of course it applies for every field, okay? So both the H and the L under SU2 transformations go like this. Clear? Okay. Now my task comes down to asking what is the how does it transform under SU2? How does this term transform under SU2? Right? This is what is H tilde, right? This thing, of course, up to an I, right? So if this is 0, this would imply it's SU2 invariant, right? So that's what we are checking. Let's see if it's 0. First of all, let me transform just the H field, okay? And I'm going to pull out the delta theta j out of all this, the actual amount by which you change the field, right? Okay. Then first, so I have to apply the chain rule, right? So then I'm not going to touch the L dagger, so that goes along for a ride. But I have a sigma 2, and since it's the H star, what happens? I get theta j star, correct? H star, right? So I just imported this over here, okay? And notice that that's the reason why I have pulled out a minus sign also, right? If I hit it on a H star, then if I take a star, then the transformation goes with the minus I, right? The complex conjugate. Okay, that's the first term. Now let me hit it on the second, the L term also. Because there's a dagger here, once again, you know, if I take the complex conjugate, I'll pull out a minus I. That's why I literally pulled out a minus I over here, right? So what happens here? Since this is a complex, because since it's a Hermitian conjugate, since I have a transpose sitting over there, I have to write the L dagger term first, then I have to write the sigma j, right? Not only that, I have to write the sigma j dagger term. You see what I've done here? Basically, I've rewritten the transformation in this way. The columns have become rows, okay? And the other term goes along for a ride. Okay. Okay. Now, let me quickly rewrite that as minus I over 2 delta theta j, L dagger and H star have remained intact, right? So I put sigma 2 sigma j star plus sigma j dagger sigma 2, okay? And I'm pulling out a H, okay? Just rewritten it. I do this because now we are going to make use of a fact, okay? In fact, we're going to make use of two things in mathematics. One is that sigma 2 star is nothing but sigma 2 minus sigma 2, Okay, you agree? Why? What is the Pauli matrix there? That's what it is, right? Maybe I'm switching the minus sign, but it doesn't matter. If I take the complex conjugate, then I get the minus of the Pauli matrix. So, that is one fact. Another is that I'm going to make use of this identity. If I take the Pauli matrix and hit it with sigma 2, okay, and then I take the transpose first, and then I don't take the transpose later. For any Pauli matrix, okay, this is true. You can go check this. It's very easy to check this. Okay. So, if I make use of these, you will notice that this term, right, sigma 2 sigma j star plus sigma j dagger sigma 2 is always 0. Okay, put these two things together. You literally take sigma 1, sigma 2, sigma 3 for each of these, put them together and you will find that it is 0. See, it's trivial when j equal to 2, right? That means I just have sigma 2 star plus sigma 2, Hermitian conjugate sigma 2. Then I make use of this, then these two basically cancel each other, right? So, but for j equal to 1 and 3 also, this turns out to be true. Okay. In other words, we have proved what we wanted in the first place, which is that this is invariant under SU2, this combination. Okay. So, indeed we have succeeded in writing the Higgs couplings to both to the leptons, to the the left-handed quarks marrying the right-handed d, and the left-handed quarks marrying the right-handed up as well. Okay. Okay. Now, what else should we write for the Higgs term? I've introduced a field. Obviously, it's going to propagate, right, in the equation of motion. So, I should write a kinetic term, right? So, the kinetic term of the Higgs, we saw this when we were talking about scalar fields, right? It's nothing but this in terms of the covariant derivative, where the covariant derivative is what? There is a G2 because it is a doublet, and it also contains it also is charged under hypercharge, and the hypercharge is 1, so I am just writing a 1 here. Okay. Okay. Fantastic. So, we are going to end this lecture by making an observation that we are going to explore as we go along to the next one. Okay. What is that observation? See, if you look at this Lagrangian, can't you see that I have actually succeeded in marrying, in some sense, a left-handed spinner and a right-handed spinner, right? Whereas if I look up just over here, I was not able to do it when I wrote it in this form, right? Because it's just a literal mass term, okay? And gauge invariance was forbidding this. But now I introduced a field that carries the gauge charge, right, the Higgs field, and so I was able to write down a term where it's all gauge invariant, all the gauge charges are eaten, and in some sense through an interaction I have married the left and the right handed fields. It's not yet a mass term, right? But there is some hope that some mass term can be obtained from this, right? Next, if you look at the kinetic term also of the Higgs field, right, because of gauge invariance I had to write down this covariant derivative, and because of that, right, what do I get? I get terms like So terms like H dagger H, W mu, W mu, and so on, right? So this makes it look like if, okay, we can replace the Higgs field with some constant, okay. I'm just going to call the constant V suggestively because that's the value we're going to use later. If we do this somehow, okay, imagine some magic happened so that you could replace the field with a number, okay. How is that possible? We're going to see how that is possible. There is a physical way in which we could do this. If you can do this, then would you agree that just like that you've given a mass to the fermions, right? The mass of fermions would go as some Yukawa, right? Yukawa coupling times the V times the left-handed fermion married to a right-handed fermion, right? And similarly, if you look at the gauge bosons, would you agree that the W also got a mass which is like V squared, right? So okay, this is just the mass, so I'm not going to write not the Lagrangian term, so I need not have written this, but you agree, right? Good. So that's exactly what we are going to do in a careful way, and this is exactly the basis of the Higgs mechanism, okay. This is where we are going to talk about symmetry breaking via the Higgs mechanism, which is applicable particularly to the standard model, okay. So this we are going to take up in the next lecture, and I'll stop here. All right, thank you.